actually come to the next stage of our workshop today. And the next big theme is international and Austrian scientific projects concerning GIS standards. The first presentation will be held by two gentlemen. The first is Jörg Hamler of the Office of Federal Government of Austria, and the second is Gerhard Rabatil of the University of Technology in Vienna. And I would just like to introduce them both shortly. Jörg is a software engineer working at the Office of the Federal Government of Austria, and his responsibilities include data management, geoinformation, and is also involved with the internal consultation for geoinformation systems. Gerhard has a background in surveying, and he's been working at the University of Technology in Vienna since 1998. He's a senior scientist in the Geoinformation Research Group in the Department of Geodesy and Geoinformation, and his research interests include spatial data quality, GIS services, and legal issues. He's also the author and co-author of approximately 150 articles, and he has supervised more than 50 bachelor's, master's, and PhD theses. Thank you.
Welcome. So my name is Gerhard Rabatil. I take the easy part. I take the bracket. I give it a brief introduction and then have the conclusions. And my colleague Jörg Hamler will tell all the interesting technical details. So the question that we have is, we have a public authority, which is the federal government of Lower Austria. They produce data sets, and they need to also provide metadata for that. And if we look at what public authorities do, they produce, or they have a legal obligation to produce metadata for their data sets. And unfortunately, they have to fill in a couple of different data sets. And why do they need to produce the metadata? Because the data should be able to be reused. So you need to know what's in the data set. So you need decent description of that. And the metadata describe the data sets. So one of the problems is that the data themselves are produced by domain experts. So it's domain experts who collect the data, put together the data sets, but they are not experts in providing metadata. So we have a big gap between knowledge of data collection and analysis and the description of the data sets. And providing metadata is quite complex. Just think about describing fitness for use of the data set. Okay, that's data quality and not specifically metadata, but it's quite difficult to assess is the data set fit to be used in a specific application. So we have multiple standards. We have international standards, we have the European Union, we may have national standards. We need to fill in all of them. So we can, of course, start from scratch for each of those standards, but that does not really make sense. So the question that he came with to me was how to avoid duplication of the work that we are doing. And he will now give a brief introduction about how we, or what we figured out, what could work and how far we got.
Thank you, very warm welcome. I want to give you a quick overview about the metadata standards we should provide in Austria as public authority. That is the ISO standards, the 1900-115, is needed for internal documentation and data exchange. It's also the oldest standard we use in our organization. It describes one data set, one service, or one data set series. It has very few mandatory attributes, about 5, and about 15 recommended attributes for discovery. It has a huge amount of optional attribute values, so it is very versatile, but it's also hard to understand for the metadata producers or the domain experts. So you have to think about the domain expert is metadata catalog like GeoNetwork or something, and this huge, a very complex form to fill out for him if there are lots of attributes to fill. He doesn't understand it. It's not his expertise. And it is encoded in XML. The next standard we have to provide is Inspire. It's needed to fulfill the directive from the European Union. It's derived from ISO 19115 from the 2003 variant, and the ISO 19139 from 2007. It also describes one dataset, one service, or one series. It's very similar, but it has a lot of mandatory attributes, around 20. It's very restrictive in what you have to provide, what you have to fill out, the order of keywords or the content of the attributes, and it's not compatible with the ISO 19115-2014. It has about 5 attributes recommended for interoperability, and it's also XML. The last standard we have to provide, is relatively new, is DCAT. It's a data catalog vocabulary, you know what I mean? It's also directly from the European Union. This standard describes data catalogs. So before we described one data set, now we describe a whole data catalog with multiple data sets and multiple sets. The main goal of the standard is discovery. There's GeoDCAT AP. It's an extension to map Inspire metadata to DCAT metadata. And this mapping is in its own standard, but the mapping is lost. So you can't exchange those rows. It has about 4 mandatory attributes and about 4 recommended attributes for discovery. And it's RDF and XML. What's the basic idea? The basic flow, how to produce metadata. The metadata is usually produced from the data producer. He has the most knowledge about the data. He fills a metadata form, and the idea is that we fill a relational intermediate model and try to reduce all 3 standards that we need, because we generate them so that they are conform and valid. To help the data producer in filling those forms, we try to extract meta information from the data itself, like the bounding box, or is it vector data or raster data, and so that the burden to fill the metadata form is a minimal. So that's minimum. Yeah, that's the basic idea. We tried that. It basically works. It has its benefits. It reduces the workload for the data producer. The metadata knowledge is not, the domain expert does not need to know something about the metadata. The knowledge is encapsulated in the mapping to the intermediate model, or from the intermediate model to the metadata documents produced. The manual input needed is reduced through automatic extraction from the attributes in the data itself. And also very important, the metadata information is stored only once in the organization. So you can report on that data very easily. You can support the form with pre-filled information, that's not really new. And also very necessary for the internal data management is you can hold more information in the intermediate model than published. Like what is the internal data source, or additional information that you do not want to publish. If you hold your data in the metadata standard and publish it, you only can fill it with information that you want to publish to the outside. What are the challenges we saw? The intermediate model has to be very strict and is not very versatile. It's as strict as the strictest standard you want to produce. In our case, it's Inspire, so it has to be at least as strict as Inspire is strict. The mapping of existing metadata, if you have already metadata information, results in potential information loss. So maybe you don't have every information, so you can't map every information from the existing metadata in the intermediate model. The standards are in certain aspects not compatible. Inspire has the concept of priority data sets, for example, and TCAT and ISO don't know something about priority data sets. So you can't fill out priority data sets and map that in every other standard. The biggest thing, in my opinion, is that TCAT describes data catalogs, and the other two standards describes data sets. So you have to produce for each data set a whole data catalog, RDF, to publish it on the outside. I don't think that's very practical. The data producers needs to fill the minimum information for all standards you want to provide to the outside. So maybe much more than they usually need to fill out. And the intermediate model is manual work, and the mappings are hard-coded. I tried to do it with semantic mapping, but I got not very far. Okay, now back to Gerhard.
So after Georg presented how far we came with the modeling, a quick conclusion. So we need to harmonize standards. We have heard in the morning that it's already 3 decades that ISO and OGC are cooperating, but we need to harmonize our standards even more than we have them now. Because the world is rapidly changing, technology is rapidly changing, so we have all new things emerging, and they need to be merged into the existing models, and everything should be consistent. If we do that, of course, that's a lot of work. Do we get benefits? Yes, because afterwards we save a lot of work. So if we do it correctly in the beginning, if we writing the standards, we harmonize things, make things work together, we save afterwards a lot of manual work. So it's things like either verbal descriptions or parameters. We should be able to decide on one, and not one standard demands one and the other standard demands the other, because then we will definitely get mapping problem. In places where we cannot avoid having clashes, how do we overcome them? We can think about different research approaches. We could use or try to use natural language processing. So if we have a verbal description, try to extract from them the parameters that we should fill into the model. That might work to some extent. In the past, natural language processing has been used, for example, on literature to identify places where some novels were played. It might work here as well, but definitely not to the full extent. Semantic translation of categories has been tried by Georg. It works to some extent, but it's error-prone still. So we will not get the perfect result. And we can try to extract as an intermediate model from descriptions of standards if we have the standards in machine-readable form. So we can try to figure out what's the same, what are the elements that are the same, which can we merge, which do we have to keep, and then, of course, there is still some manual work to find out, okay, this is more or less the same as this, it's just in different terms, this version. So, of course, we have small step but that's scientific work. We worked on it for half a year approximately. So the projects in the morning were several years mainly, or half a decade or something like that. Scientific work, usually we're looking at simpler questions, and sometimes the answers are still not. Yeah, the answers to everything. So thanks for your attention, and feel free to ask questions after at the end of the session. Thank you.
Thank you. Good. Our next speaker is Mr. Christoph Berger, and he is the CEO and co-founder of a company in Vienna called Spatial Focus.
Okay, thank you very much for this kind introduction, and welcome everybody here online and offline. And thank you for giving me the opportunity to tell you more about our company, Spatial Focus, and about our latest developments. Also in the room, we have Christoph and Sebastian, and we're happy to answer your questions after the session or also by our roll-up here on the side. So let's start by giving a short introduction about Spatial Focus. We founded it in 2015, and we are based in Vienna. And we see ourselves as kind of the combination of software development and geospatial know-how. So the main pillars of our work are developing web and mobile solutions, as well as modeling and consultancy, everything in the field of GIS, geodata, risk observation, and software development. Today I want to tell you something about our latest solution. It's called SDI as a service. It's a scalable and fault-tolerant spatial data infrastructure. As the name already suggests, it's provided as a service. So it's cloud hosted, and for a potential customer, there's zero configuration and no coding involved. Let's step back a bit and think about how a typical GIS project looks like. And what are the requirements? So in the past, we've worked on many projects, and all of them had a very similar setup. So for all these projects, we needed some website that is based on general information about the project, some news, some contact information, maybe. Then typically, as it's a geospatial project, we have some geodata. We put that in a catalog. It can be some intermediate data that is shared within the consortium. It can be some data that is the final product of the project that has to be shared with the general public as well. We typically display those data sets on an interactive map. So the main topic here is again the hosting. So where do all these services and where does the data sit? We also have to think about data access. Data has to be secured, but it also has to be made available to certain user groups. Maybe the internal project partners, maybe the external contributors, maybe the general public as well. And then typically the development part came in, which is to automate some workflows and provide some help to reduce the manual work and the effort of concluding these projects. So this brought us to thinking about a better solution than to develop everything from scratch for each of these projects. So we came up with this SDI as a service. So let's look at some features. It provides viewing, downloading, and publishing services, everything built on top of open source tools that are well established. The whole system is fully interoperable with the standard desktop or WebGIS tools due to the use of open standards. We are providing an admin interface for the workflows. So for just automating manual work as well as building some high-level abstraction for people who don't want to go into detail with the underlying tools. It also comes with a monitoring dashboard, so you get some usage statistics, some statistics about the liveliness of services and the status of different services data sets and such, and some interesting metrics as well. The whole system is extensible and is modular, so you can easily replace one module with another one. It can be extended by developing more features into the admin interface, automating more of these workflows. And then what combines everything is this content management system in the background that is there for managing the web pages and managing the content of those web pages, and then making it publicly available. So if we look at this graph, it gives a schematic overview of this SDI as a service. So the whole system is built up on this admin interface, and we can see the CMS and the dashboard. And below that, we have our typical standard GIS tools. We have a PostGIS database for storing the data. We have a GeoServer for making our WMS, WMTS feature service available, publishing everything. We have our GeoNetwork for the metadata as a data catalog. And we have, for example, MapStore for displaying these interactive maps. But as indicated here in the graph, there can be many more. And since it's extensible, scalable, and replaceable, everything there, which sits below this interface, can be replaced by any other open source tool that is attached to this interface. So this already brings me to the final slide about some future outlook, our future roadmap. Of course, we're interested in integrating additional modules. So this previous slide only gave an example of what is possible, but of course, there are many more tools out there that should be integrated in the solution. There's also the idea of automating more of these standard GIS workflows, making it simpler for the user and integrating more tools to make your life easier. And then the last point, there's an open source client currently developed by the Environment Agency of Austria, which combines a graph database with a WebGIS solution. So we have our ontology, we have our knowledge graph, and together with a WebGIS, we can interlink those two. And we can navigate both on this knowledge graph as well as on the map. And navigate through the nodes and see the nodes. The two tools are something that is very bad in the near future as soon as the tool becomes available. So this already concludes my presentation. Thank you very much for your attention, and we are open for any questions afterwards and also at the dinner. Thank you.
On to our next speaker. We have already introduced him. The Spatial Temple Asset Catalog, an ISO method to describe spatial temple raster down publications. And we'd like to welcome once again John Governor from the Office of Federal Government of Governance.
Hello again, and thanks to my second talk. For those who don't know, Lower Austria is the area around Vienna. It's one of 9 provinces in Austria, and from the area is the largest province. The problem is, I stated it in the talk before, the EU, the European Union, mandates the directive 2019-1024, but I also want to read it. I don't recommend it. That we have to provide our data, our spatial-based data to the public. And we have to make it available for reuse in a machine-readable format via APIs and as relevant as bulk download. Usually, we publish our data as services, but not as bulk downloads, so that's really new for us. And we don't want to provide 2 systems, one to make an API and one to provide bulk download. The problem is, Lower Austria is about 19,200 square kilometers area, and we manage our data in tiles, and one tile is about 1.25 square kilometers big. So our data products, our raster data products, have around 15,500 tiles. We have around 40 raster data products, orthophoto, the digital surface model, the triangle, and the derived products like hillshades, slope, aspect, and so on. So we have to host about 650,000 tiles to the market. The characteristic of this data is the data is captured in blocks. So if you fly this the airplane, you only capture a certain area over a specific time. So the full coverage is for ortho imagery around 3 years, so that we cover the whole Lower Austria, and for the laser scan about 10 years to cover the whole area. And we have historical data since around 2002. Each block has potentially, over this time since 2002, different resolutions. We have different bands. In the beginning, we have RGB. Now we also have infrared, for example. It is flown with different scanners. So we have different lineages for each data product and for each block. And for the derived data, usually different process steps over time, how we created the data. So we should provide 650,000 metadata sets to describe each tile. It's around 30 terabytes of data. If you have 650,000 metadata sets and push it in a geo network, nobody will find it. It's not a solution in our IT. So we did some research and found Stack. It's relative new standard. It's an OGC community standard. The idea was around, as I read on the website, around 2015. And it's compatible with the OGC API features standard. It has a very minimal, stable core metadata model with lots of extensions. How can you describe the data, like for satellite data, for point clouds, you can describe projection information and so on. It's relatively easy to create, and to host this data, you can host your data static, so you generate it, copy it on a web server, and you can provide it to the public, and also the metadata, so you can generate it in a static manner, copy it to a web server, and that's it. The stack core objects, the core of the standard, is very minimal. You have a JSON file, it describes the catalog, you have an idea, a description, a type, and links to other objects. You have collections, it's like a folder in the file system, where you can push items with the same attributes, unfortunately the same set of attributes. Also, this very minimal attribute set, you can make nested collections, and you have items. An item describes one asset. An asset would be, in our case, a tile from the auto imagery. Usually, it's recommended to use cloud optimized GeoTIFFs or formats that can be consumed from the cloud in a graphic way. Or escape read in our case for the terrain data or the surface data. The items and the collections are GeoJSON, also a standard everybody knows. And it's relative, the tooling around is relatively common. Everybody can produce GeoJSON and consume GeoJSON. To provide additional metadata, there are stack extensions. In our case, I took the height information, would be the raster extension. You can describe additional metadata per asset, so per tile. You can describe each band, no data information, the spatial resolution, and so on. And you can filter and discover with these attributes and this information the tile you want from. So core standard and the extension for the data you want to provide. The question was, we also want to provide ISO metadata. We already have ISO metadata for our raster data information on a block level. So for each block, we have an ISO metadata set. And how can we combine those two? And the stack standard allows to provide ISO metadata as assets. So you can discover also your ISO metadata XML and provide it to the people or organizations that download the data so that they can reuse it. It also works that you link to a catalog service web, a CSW, so you don't need to publish your ISO metadata in another manner, so you can reuse the existing infrastructure to provide ISO metadata on the block level, and for each tile, for discovery, the stack metadata. So what's the outcome? The stack metadata is, as intended, well suited for discovery, filtering, querying multiple types of data. You can describe raster data, you can describe point clouds. Usually it is used in the satellite industry to describe satellite data. The ISO metadata, in contrary, is well suited to describe the data in detail. The fitness for use, can I use this data? I can describe the process steps, the quality, and so on. All this information you can't provide via the stack metadata. So you have more and extensive and additional information on the fitness for use in the ISO metadata. But it's not well suited for discovery, in my opinion, in the usual tooling on a tile level with this extent of data we want to provide. And stack allows the ISO metadata to be added as assets. There is a specific role for the asset. The role is called ISO 1900-115. And on collection level, you can provide, for example, a series, a metadata data set about the series. Okay. That's it. Thanks for your attention.
Good. on the program, we have a coffee break. We'll take a coffee break. No, no, we're going to push through. How do you guys feel? Shall we vote?
Do we need a coffee break or
What a bathroom break. Don't worry. You want one?
hands up?
You want one?
Okay, so 15 minutes.
So you want a break? Yes, he wants a break. Well, he spoke a lot. I think he needs a break.
It's for 15 minutes.
Yes. Okay, in 50 minutes, we will meet here again, and then we'll finish up.
You are.
Lustige ist jetzt auskommen, die Aber das ganze Thema Data Access ist man sieht dann, nein, das ist bestimmt nicht. Genau. Ja, genau. Genau. Wir sind genau. Und dann auf der anderen Seite wieder zu hören, wir alle, gib mir alle, dann macht
Nein, aber es interessiert ihn was.
Genau das Thema endliche Gast. So ist es, ja, weil jemand trainiert, sagt, okay, bin ich wieder so tragisch, muss das okay, was bin ich ja so wenig. Da gibt es wohl die Historie.
Danke für die Unterstützung. Bitte mir noch
Schau mal auf die Zukunft. Gentlemen, please take your seats. We only have one or two ladies here. Good. We are nearing the end of today's discussions. Our next speaker is Johannes Schultz from the University of Technology in Graz. Johannes is an associate professor at the University of Technology in Graz, and he is the head of the Geoinformation Research Group in the Department of Geodesy and Geoinformation. He's also part of the Division Geographic Information Science in the Austrian Academy of Sciences. His research focuses mainly on geosemantics, spatial linked data, geo-knowledge graphs, and geo-artificial intelligence, which is one of my favorites. He's also interested in spatial optimization and spatial agent-based modeling and simulation. Today, he will be explaining us more about using knowledge graphs for the semantic annotation of spatial phenomena. Thank you.
Well, hello everyone. Thanks, Annalena, for the kind introduction. Yeah, the topic sounds a little bit theoretical. I have to admit, well, it is. I won't bore you with any formulas or any super technical, let's say, details, which might get you all a nice nap in the afternoon. So let's stick with nice pictures and nice, smooth and easy explanations here. So what I want to get across today is basically like short motivation, introduction. I want to get to know, get used to knowledge graphs, what are general knowledge graphs in a nutshell. Then I would like to somewhat stress the fact that standardization is a topic that's also relevant for geoknowledge graphs. Although some of you might say, oh well, those two topics are totally apart from each other, are on two either ends of the world, but in fact they aren't. And then I would like to explain, or would like to show you some examples of what we actually do and did at a research group. That's basically what we are about to see today. So we have some geoknowledge graphs for supply chain, visibility, for digital humanities, and also for English geography and smart manufacturing. That's basically what we're about to see right now. Yeah, starting off with a little bit of motivation. The thing is, and everyone knows that we are drowning in data, right? That's the issue here. And the fact is, and it's also underpinned by several publications that we can see, or that we have, most prominently the one paper from Harvey Miller and my good child, data-driven geography, that explained this turn from data scarcity to the data deluge, more or less. And what we have to do is somehow we have to select the data that are relevant for the particular question that we would like to answer. And that's a hell of a task, because, well, selecting the right data, getting the right data, with the right methodologies and with the right, the appropriate, let's see, algorithms, that's a huge task in itself. You know it, so there's tons of, let's say, social media platforms like Twitter, like Facebook, whatever, Foursquare. There are tons of open data platforms available where you can get data on various, let's say, topics, on various spatial phenomena. But the problem is how to interlink those. And that's the biggest issue that we are facing at the moment. And what can help us to do so, and what can help us in order to get the sensible answers, or to get the right answers from those data, is more or less geospatial artificial intelligence. That's, in a way, the umbrella term, in a way, to all those technological advancements that have happened in the last couple of years. And Christoph Janowitz, who is now appointed professor at University of Vienna, since, I don't know, 1 month or 2 months ago, so let's think 1 month, half a year ago, or whatever. But most of you know him that he was professor at University of California, Santa Barbara, and he basically coined this term with a couple of others from him. And the GeoAI basically encapsulates all, let's say, relevant scientific methodologies that deal with data science in a way that is geared towards geospatial intelligence and stuff. So I won't bore you too much with that one here, but in essence, what differs AI from GeoAI is that location is the key factor to that. So location is the glue to all that data sources from different vendors that we have. So location is the glue that basically helps us to integrate different data together, and that can help us to, in a way, analyze the data in an appropriate manner. And this is really helping us, and this is really a step forward, basically, because spatial explicit models, basically, are AI models, are way faster and way more, have more explainable power than classical AI technologies or machine learning technologies. And you can see this pretty easy when it comes to image classification or any other geographic question answering methodologies. On the right-hand side, you see a picture from us. That was a project from us rather recently. That was a GeoAI algorithm that we employed at the UMass for an annual Mars mission in the Negev desert in Israel. So we had played the Mars mission with the Austrian Space Forum, basically. So we had analog astronauts that were deployed there. We had a rover, and we calculated, for example, with GeoAI technology, we calculated a traversability map for the rover. So there are rocks, there are cliffs, there are bushes, shrubs that cannot be traversed, for example. That was what was the result of that. But in order to, let's say, give GeoAI the push that it really works well and it really flourishes in a way, you need to do something underneath those technologies or the algorithms, basically, in order to get them working pretty well. The thing is, first of all, we need to think of several things that are necessary at the core, which are, for example, semantics, linked data, and basically semantic web. So what we need to basically integrate data sets in a, let's say, real-time way or in a let's say automatic manner, we need to come up with linked data and knowledge graphs. This is interesting because otherwise it's pretty hard to basically integrate those data. So you need semantics, you need linked data, you need the semantic web in order to function. And this basically what we see here is the linked data stack, semantic web stack that we have here. And most important here is that this semantic web stack, you could also extend it to geo semantic web stack, requires some sort of semantics. Without semantics, you're all lost, basically. That's the core. So you need some semantics to say what is there and how do these objects basically interact with each other. Without that, let's say, knowledge that you hand over to the system is basically lost. So the system is only as intelligent as the models you give it, or as the semantics you give it. For sure, if you have ontologies or semantics, you can always infer knowledge based on existing knowledge, that's for sure. But nevertheless, you have to give the semantic web kind of a, let's say, full picture of what's ahead of you or what the real world is all about. So that's pretty necessary. And we've seen in the last 20 years, 25 years in research on ontology. So there are several works on ontologies. I don't want to suggest you with that one here. So you have seen it in the mid-90s. It basically started, or even Andrew Frank started earlier in the 80s with databases. So that was a long development, basically. And right now we are at the stage that we tend to include ontologies in knowledge graphs. So knowledge graphs are pretty nice. So basically we describe the world as it is. So that's digital representation of the real world. It defines all the classes, relationships similar to an ontology, but what it explicitly does is it also includes all the data with it. And that's the fun part here. So the easy question here is, for your knowledge graphs, you have an ontology, so you have a description of what's in reality, added with the data, with the actual data. And that basically what a knowledge graph is, why a knowledge graph is so special. Because you can basically query data with the help of the ontology, with semantics attached. So that's a really fun part of that. And you'll see that in some seconds, how we do it in several projects. For sure, knowledge graphs really work well if they are, say, coupled with the latest, let's say, semantic web technologies, for example, NoSQL databases, Christopher told us today with the Neo4j database. So those are all things that work hand in hand. And fun part is here that compared to classical OWL ontologies, you see that knowledge graphs are, let's say, faster when it comes to reasoning capabilities. So it's really a step forward because you're way faster in analyzing big data sets than with classical, let's say, reasoners that are built in, let's say, ontology engines. Yeah, and what does all this have to do with, let's say, standardization? Well, that's pretty simple. So I just listed a couple of items that could be of interest or that are of interest in particular. What do geometry graphs and standardization have in common? Well, that's pretty simple. So first of all, geometry. That's the simplest thing, especially you need to source the geometry. Very often you have geographic domains that are stored or that need to be analyzed, kind of. So definition, what are geographic names? The asset tiers, for example, all that stuff that's pretty interesting together with knowledge graphs. But you need some, let's say, theoretical foundation to store geographic names in a proper way. Addresses are also of interest, then all kinds of temporal schema, because like very often with knowledge graphs, you do think that the world is static, which it is not, in fact. Meaning that we need to include some temporality, the temporal dimension into knowledge graphs to see processes. Metadata are of interest. The thing with metadata is, in a classical way, as Aristotle defines it, they are like a separate data set, kind of, right? With linked data and with, say, graphs, it's not a separate data set anymore. You would more likely integrate it in your knowledge graph. So we recorded. Fine. Yeah. Let's go on with that one here. So the thing is, metadata can be integrated into the data set itself, and then it can be queried. So it's not like, oh, you have to think of metadata. Who wants to play around with metadata? And the one that raises his hand last is the one that has to deal with it. Sorry for that. But now it's more integrated, and you cannot get over metadata, so you have to do it in a way. And you can integrate it, you can basically do something with it. So that's positive, that's good. Another thing is place identifier architecture could play a role, and for all ontology and the standards concerning ontology and other handling are surely of interest for all that. And now the fun part, examples. So I don't want to bore you anymore with theoretical issues. We've done some things with knowledge graphs. I mean, well, I'm not the only one. There are other ones like this stuff, and tons of other people who do really great stuff. So we are just like on the edge and doing some nimble projects here. So this was basically knowledge graphs for supply chain visibility. This was a master thesis in conjunction with University of Applied Sciences of Austria. That they have like a specific research division called Logisticum, which deals with logistics. And what you can do, you can integrate a whole supply chain with different actors here in real time with an ontology, with a knowledge graph. And you can integrate all those data and then you can ask spatial temporal queries for the whole supply chain over all vendors that are contributing to the supply chain, which is really a step forward. So you can ask questions concerning carbon footprint, how long did it take, what is the distance of the goods transported, and all that stuff that you would like to do. So that's really fun, basically. We also published on that. Second example that I wanted to bring up here, I want to discuss here is digital humanities. That's a topic that most of you might have not expected to be here. Digital humanities is like history and all of the humanities science, and we can basically support them with our geoinformatics knowledge and our technologies here. So that's really fun. We have a long collaboration with Carl Grossman from University of Pittsburgh on a lot of historical gazetteer here. And what he does, basically, they have a gazetteer of historical placements. It's really fun. And even more fun is if you can connect those placements with phenomena, historical phenomena that happen. For example, here is on the right-hand side, the upper figure here is the travel of the monk Huang San. That's a Chinese monk, basically traveled through all China, India, and all those countries in Asia. And when you can connect his travels with places in a spatial-temporal way, you could also see, well, which other people could he have met, which other events could he witness, for example, and stuff like that. So that's really nice. So you have to bring all those data together. And a colleague of mine, Francisca Rigo, she's my PhD student at our group, she did with a knowledge graph. And that was pretty nice to bring all that together and then do spatial temporal queries, spatial temporal analysis, and all that. So that's pretty nice. And yeah, so that's it. And the third example that I wanted to bring up, also more a niche example, but a very, very neat one actually. We started this work on indoor geography and smart manufacturing 2015, so that's quite old. That was a PhD student of mine who worked at Vienna Technologies, which is a semiconductor. So that's a special manufacturing environment with clean rooms and all the regulations that come with it. So you see that they are all masked up in specific clean room clothing. The room is, let's say, pretty narrow. Everything looks the same. And the thing was, we have in 2015 we started to generate a knowledge graph on the whole indoor geography and on the manufacturing assets. So machines, all the, let's say, wafers that are produced there and stuff, in order to support smart manufacturing with the help of geosemantics. That was pretty successful. Yeah, finished in 2018. And I just wanted to bring this up because I think this is, well, a pretty nice example of how this might work. Yeah, concluding, I don't want to go into too long. So first of all, geoknowledge graphs are really, a well-suited technology and well-suited, let's say, approach to basically store spatial data and connect spatial data with each other with the help of semantics and to analyze them. They pave basically the way for GeoAI and they help to flourish, bring GeoAI on. And for sure, what's necessary for geoknowledge graphs, though most of you don't think of it, is you need some, let's say, theoretical foundation, you need some foundations, you need some definitions that are the same, that are standardized, and that's where basically the standards come into place. So here it is a solid semantic foundation, standards can play a vital role in that. Yeah, and that was it for me. Thanks so much, and I'm looking for questions. Thank you.
Thank you very much. Thank you, Johannes. You did not bore us at all. You were very fast, and it was very informative. Good. We now come to our last speaker today. And he is all the way from down under in Australia, and he will be joining us online. Hopefully, let's see if we get our infrastructure correct, we can set it up. Of course, it's very early in the morning in Australia. Okay, it doesn't seem that Matthew is online at the moment. So we will maybe just skip ahead for now. Should we have a discussion first? Yeah. We now have some time for discussion on the scientific projects that we have actually seen present in the last section. Are there any questions from the audience? Come on, guys. Yes, please.
Thank you very much. Yes, you're from Denmark. As for the last presenter, have you experienced any problem with bandwidth if you combine a large number of sources into one knowledge graph and then have to produce the final result? I mean, it's a different location. What do you mean with bandwidth? I mean, that you need to extract data from one source and then another source at a different location, and then combine them and then make your queries and analysis.
Basically, the thing that when it all comes together, it's you need it.
Yeah, I didn't understand.
Yeah. So I mean, the question was, if you integrate data from different sources, from different vendors in a way, how do you do it, or what's the bandwidth? What are the obstacles, basically? Yeah, the thing is, what you need to do, you need kind of, and there are several strategies to do that. First of all, you need to define both data sets in terms of ontology. Otherwise, it doesn't work. So you need to have some common sense what is meant with which, let's say, column, for example. What is a specific feature all about? What does this encompass? What's the definition of that? So you need to basically match those things to a single ontology, or you use predefined there are ontology design patterns, for example, which are standardized, which you can use where you can map your data sets to that one ontology or different design patterns which you can reuse, and then afterwards you can bring it together. You cannot do it like, oh, we have two data sets, we push it into one knowledge graph. That basically is problematic because you have two, let's say, dislocated data sets that don't have anything to do with each other. So you have to combine them in a knowledge graph. And in the knowledge graph, you can also include the ontology as, let's say, abstract nodes, abstract patches, whatever. And then you can connect the abstract nodes with the instances, with the data sets. And say, oh, no, this data point here, or this node here is feature class road or house or whatever. And from the other one, oh, this is a house as well. Or this is a, let's say, multi-storage house, or this is a residential house, or this is like a commercial building, whatever. Yeah? And this is how you do it, basically. So you have a connection then between those two via the ontology, the abstract nodes. That's basically how you do it. Yeah.
Any other questions for yes?
I'll stay there. Following up on that question, I mean, it's a two-part question. The first question is, to what extent classic technologies providing data, but utilizing JSON LD gives you the proper food for further processing? So I mean, there you've got the mapping to at least the ontology of choice of the data provider. You may need to do some cross-mapping to what you think is your ontology. So that's the one half is how does that support it? The other half is taking that a step further. If you had 5 distributed geospar planes using the same system, would that function do the query scale across that? That's why I always lose trust in semantic technology.
Oh, first question.
First question, LD. How would having things like Inspire with an LD context in the background make your life better?
Yeah, that makes life better, basically.
Can you please tell JRC that I'm working on it, but I need to push from the other side.
Okay, that does make life a little bit easier, right? Sure, if you have a mapping, if you have that makes life easier.
Related to that, I mean, you're familiar with Inspire.
Yeah.
Would mapping to the Inspire data model get you halfway there? It's not an ontology, but it's a really quick win. That I have a flying chance of somehow getting shifted in. And I mean, it's far from perfect, but it is way much more than we have now.
Well, it would be quite a detailed look at it, but in fact, anything that improves the status quo is better. Let's put it like that. So if you have a mapping, it's better than what we have at the moment. Of course, I mean, it might not be perfect, but it is better than it is at the moment.
Better than guessing open government data.
Yeah, that's always better. I don't know. Yes. So if you have something, that's always good. I mean, you can refine it, otherwise that's no problem. So you have to, that's the beauty of knowledge graphs. If you extend the schema, or if you alter it, say schema, say ontology, semantics, you change it, you don't have to trash, you have to dump your whole database and build it from scratch because the schema changes. If you do this in an object relational database, you're screwed. In a graph database, you're not screwed. Just add some more nodes.
Okay, but now we get to the second half of my question. How does all of this perform and scale? Because I mean, I've been following it for 20 years.
Yeah.
It would be my direction of choice. But the only option I've seen is that everybody buys Oracle triple stores or
Scaling is still an issue. I mean, the only thing that I have seen right now is, for example, concerning scale. So Crystal Yanowitz, they came up with a genealogy graph basically on the world. So they integrated, I don't know, 12 terabyte of data. I don't have the link, I don't memorize it. But they have published it. This was an NSF grant. They're still working on it with $4 million funding, $1 million. And they have integrated, I don't know, 12 million triples or something. And this scales pretty well, so I tried it out the other day. And
running on what technology?
I don't know. We have to look it up on the website.
And single endpoint or distributed endpoint? I'm
pretty sure it's distributed. So they have more.
I'd really like to know the technology.
No, I'm pretty sure they have it distributed because they will cope with the load. So they have it distributed on several servers. That's what I'm pretty sure about. I have to read that because it was published like, I don't know, 1 week ago or so. And it works sure pretty well. It was a project together with ESRI, for example, and several other companies. And yeah.
They're really interesting to explore. Is this proprietary software behind it? Is this open source?
Now, I think it's more or less open source, but I have to look it up. I don't know what they did. I just had a look at the interface, tried it out. So they have data from US Forest Service, US Geological Survey, whatever you can grab in the US is basically integrated there. What they did, they have mapped all the data to S2 cells. So they have a cell-based approach, and basically you can query each cell, what's there, and you can query all the different data sets that are there. And that's all integrated in a single knowledge graph, genomics graph.
But that brings me to a further question. I didn't ask, it didn't fit, but since we're playing for time here until Matt wakes up, have you seen the application of similar type of processing, but not vector point data, but gridded data? Instead of vector point data, as you've been showing, doing this on the various gridded data sets, coverages.
Which data sets?
Gridded.
Gridded. Oh, for example, you have the gridded data set are a little bit of a problem here. Basically, those things work best with vector data. So also those S2 cells that Christoph is referring to are basically a cell-based approach. I mean, they mapped. So they map basically all the vector data to those cells and said what's on this cell in particular. Of vector data. So basically, what I've experienced with is vector data. I have to admit that's where what my profession is or where my interests are. I don't have too much experience with gridded data. We have played around with it for the European Environmental Agency a little bit. And it turned out basically that the data volumes are pretty high. So that's sure a problem here. So you have to think of redundancy in terms of endpoints in order to cope with the traffic that's coming up. Yeah, so that's surely a problem. But basically it should work as well. But well, no one has really ever tried it out. Even in
Your project starting this summer, so that's why I'm curious.
Sorry?
Kind of Horizon project starting this summer,
Really?
so maybe next year I can say more, but
Yeah, it would be
if I'm
interesting.
curious, anything I can learn right
Yeah,
now,
sure.
I'm fully
Yeah,
there.
we're interested in this as well because we started some work on that as well a couple of years ago, and well, it stopped somehow.
I will contact you and we'll share
Yeah.
our voice.
Perfect. Thanks much.
This one now, yeah.
Okay, Let's see if Matthew Purse is online, all the way from Australia. Matthew, hi.
Ah.
Let me see if I can get you. One moment.
Yeah, no problem.
This camera is on. Can you switch it on so we can see him? Matthew, are you there? Oh, there it is.
Yep. Can you hear me?
There it is.
Yeah, it works.
Oh, that's good. That's good. All right, let's see if I can share my screen.
Okay.
Oh, no, it says yeah, not quite ready. All right. So it looks like the existing screen share needs to be closed before I can share mine.
Okay.
Sorry.
Yeah, that's okay. All right, let's give it a go now. Okay, can you see my screen?
Yes.
Perfect.
Fantastic. All right. Now, do you want me to just dive in, or how do you want to do this?
Yes, Matthew, maybe you can just start off by introducing yourself. We know that you're from Australia. We know it's very early where you come from. Please just, thank you.
Yep. Okay. Yeah. Hi. For those in the audience who don't know me, I'm Matthew Purse, co-founder and CEO of Pangea Innovations, founding co-chair of the OGC DGGS working groups, co-chair of the OGC ISO TC211 JAG joint advisory group. So a man of many hats. Yes, and I would have loved to have made it back to Vienna again for this, but logistics and other factors didn't permit. So I'm beaming to you live from rather dark Canberra at the moment, and yeah, so I guess the main purpose for me to talk to you tonight is, or today for you guys, is to give you a bit of an update on what's been happening in the discrete global grid system space. I think it's been a little while since we've done one of these seminars for the standards in practice, and so yeah, so I thought I'd just touch on things. Let's go just as an overview. I'll touch a little bit on some of the spatial data problems, because especially for those who may not be as familiar with discrete global grid systems as I am, these problems come to the core of why discrete global grid systems are a valuable and important technology to be embraced. So I'll touch a little bit on that, hopefully quickly. Then I'll give a very brief overview of the DGGS, of what they are and the why and wherefore. I'll give you a bit of an update on our standards roadmap in both the OGC and ISO. And then I want to round up with a discussion around OGC APIs for discrete global grid system, which is an area that we're, as a working group, we are putting a lot of effort into right now. And it, yeah, as I'll explain later, has a very core and key role to play. So let's start with see that or not. There we are. A bit of a trip down memory lane of how did we get where we are in regards to spatial data and spatial data technologies. Well, we started with our, I guess, experiential knowledge of the physical world around us, and some of the early philosophers and scientists worked out that we were actually sitting on a ball rather than a flat disk or a flat plane. There was a big challenge though of, well, how do we represent this world that we stand on and live in a way that we can model it and convey it. One of the, I guess, the seminal pieces of work actually came from Leonardo da Vinci in the early 1500s, where he developed a way to map in, I guess, a precise and area preserving way a map of the Earth onto a flat piece of paper, and you can see a representation there of the Mappa Mundi, which really was the beginning of the whole branch of cartography and surveying. We've progressed on to that, and that led us to the wonderful world of cartography and paper maps, and then and they served as, and still do serve, a valuable purpose till today. And in about the 1950s, with the advent of the digital computer, a few innovative and forward-thinking people thought, well, why don't we try to get these maps onto computers? And so they set about doing that, and were constrained at the time by the capacity, the technology at the time, the computer technology at the time, and so a certain set of choices were made that were efficient and useful at the scales and at the time, at that time. Really what they did is they put a 2D paper map onto a computer, and in doing so created the raster vector divide between the way we store and manage spatial data in this GIS context. But the thing is, with computers, everything's virtual, and it didn't take us that long to figure out that we're not constrained by dimensions and 2D in computers. We can actually represent things in 3D. And so we've now got the sort of the tools to create these virtual globes and digital globes that are really accurate inside a computer. But we have a legacy now of the pathway from 2D maps into, and the raster vector divide into sort of the 3D world, which is actually now holding us back. So the elephant in the room is that we collect spatial data in real world context. Everything that we observe around the world is in real world context. And by following the GIS principles, or the conventional GIS principles, first thing we usually do is we flatten that data out so that we can put it on a map. But we're not constrained by that anymore with computers, and that flattening is actually now what is constraining us and holding back the realization of the digital twin. And so on the right hand side here, we've got on the left hand side we've got the elephant in the room, which is this problem of projection. On the right hand side is an example. Well, we've got an orange, two different oranges. One's whole, one's squashed. They're purely representations of each other. But if we're dealing with a whole bunch of different data which we want to combine in real world context, it is difficult for us to do that at a global scale from this projected space. And there is another even bigger problem, and that is with the volume of data that we are collecting, the tsunami of data, the big data problem. Now, a lot of people have been sort of saying, well, look, we just throw more computers at it, throw more better, faster, smaller CPUs and memory, and we can solve this problem. We can just expand our GIS processing, and voila, we can do the job bigger, better, much more data. Problem is the physics doesn't work that way, and we actually in the early 2000s we hit the tipping point between where we were actually able to just throw more compute at the problem and see a dramatic increase, and the actual physical limitations of Moore's law. And so this is a really big problem as we go forward, and we want to try to realize more and more complex problems and more real world context scenarios that require a huge amount of data. And we're already beyond the limits that will allow us to do it. And so the question is, how do we do that? Do we just give up? Or do we start to think outside the box? Do we rethink the way we deal with spatial data and try to work with it in a more structured, consistent, and I guess smarter way, where we can still use all of that data, but we're just using it differently. And this is where discrete global grid systems really come in. So what is a discrete global grid system? A DGGS is a digital Earth reference model. It is it's designed to be an information grid system, not a navigational grid system, although they can be used for that. The primary purpose of them is to be an information grid system. Through the OGC and also ISO, we've come up with a concise definition of what a DGGS is, and that is a spatial reference system using a hierarchical tessellation of cells to partition and address the entire globe. DGGS, they're characterized by their properties of their cell structure, geoencoding of the indexing, quantization strategies, how data is mapped to them, and the associated mathematical functions. Now, the whole idea of this is to provide a consistent and stable spatial structure that does not require repeated computation in order to figure out where you are. So if we take a look at, well, what does this really mean? So here's my DGGS on a page side of things. So DGGS are comprised of a number of components. First and foremost is a way to tessellate the surface or in the higher dimensions, the volume of the Earth. Now, there are many different approaches to this. One of the most consistent, particularly for equal area or equal volume discrete global grid systems, is the use of Platonic solids. And so we've got the 5 Platonic solids here: tetrahedron, cube, octahedron, dodecahedron, and icosahedron, all being symmetrical, equal area representations of a sphere or a spheroid or an ellipsoid. Now, DGGS starts with this base and then applies a hierarchical refinement of these original cells. Now, as you'll see here, we've got different polyhedra. So we get different structures or different cell, like the properties, styles, flavors, depending on where we started in constructing a DGGS. So if we started with a cube, we generally have square style zones, is now the term. If we've dealing with a triangular based polyhedra, we generally end up with triangular type cells, and those triangular cells can then be further refined or amalgamated to create hexagons. The use of hexagons provides well, that flavor of DGGS provides a very consistent and unidirectional close packing of cells, and so there is, depending on your use case, that style of DGGS may or may not be of benefit. Now, one of the key things to a discrete global grid system is that all of these cells at all of the resolutions that they're defined in are all assigned a unique identifier, unique index. And this is usually, not always, but usually defined on some regular arrangement. In most cases, it's a space filling curve. What we're seeing here is a Morton or a Z curve. But the idea is we have a consistent and stable arrangement of these cells and the indexing, which allows us to convert these complex arrangement of zones or cells into one-dimensional arrays. So this allows us to simplify multi-dimensional complex analyses into a series of one-dimensional array processes, which computers really like. Like I said, we've got a hierarchical structure. An example of that here using square cells is there is a fixed relationship between the resolution levels of a DGGS. And so because that is known and that is fixed, we can apply simple sort of graph theory to traverse up and down the topology of the DGGS structure, utilizing the cell, the zone indexes. And because each of these, at these levels, the cell structure and the shape, the unit, or the atom of a DGGS is the same, particularly when we're dealing with equal area DGGS or equal volume DGGSs. It means we can rapidly do analysis on these things in a parallel context. So they're really well tuned to cloud computing, high performance computing, where you can actually throw an analysis at 50 million cells, but do it all in parallel, and know that you've got that you don't have to reconcile differences in area. You don't need to ensure that your area normalization is actually being done correctly, or that you're tracking your resampling errors through multiple steps, because you're leveraging the consistent structure and nature of a DGGS. And so that makes them highly scalable, and presents a very valuable and potential way to sidestep and get around the problem of Moore's law. So the DGGS standard has been around for a little while now. The version 1 was published in 2017, and last year we published version 2 in conjunction with porting the OGC standard across to ISO, as ISO 19170-1 being part 1. So last year we published part 1, which is the core reference system plus and operations, plus the definition of an equal area Earth reference system. We are currently in the drafting process of parts 2, 3, and 4. 4 is almost complete. So part 2 is equal volume. So moving from cells or pixels to voxels, 3-dimensional. Part 3 is spatiotemporal DGGS, either a surface or equal area 2D DGGS plus time, or a 3D DGGS plus time. So we're working on the specifications for those, and the one that is currently quite well advanced is the axis aligned DGGS, and this is recognizing that there are grid systems out there that originally were excluded from being considered to be a DGGS because each of the cells were not equal area, and which presents a problem for analysis, but for discovery and partitioning of data isn't so much of a problem. However, they fundamentally have the same topological operations and topological structures, which is consistent. And so we then after a bit of deliberation, we went, actually, they actually are a type of DGGS. And so we're in the drafting process of specifying what that actually looks like. Now, these activities are being driven through both the OGC and ISO as joint working group activities. And the last one here, which will lead me into my close, is the OGC APIs for DGGS. So we're getting on the bandwagon of OGC APIs, and there's a very good reason for that. I apologize for the wall of text here, but I'll just quickly step through it. So the thing about the existing specification, the published standard or abstract specification, is it defines really well the DGGS reference system and the core topological functions. That's great. It allows someone to be able to build the back-end architectures and infrastructures to support all of these things. But we still have the problem of how do we access those DGGS infrastructures? And prior to the to the OGC APIs, that's been a major problem of going, well, how do we actually do that? Do you write a bespoke tool and then have everyone have to come to yours and use your special API, which just presents the same old barriers that we've been experiencing in sharing data across the web. So this is where OGC APIs, or more generally open APIs, which they're based on, come in. They're a very good way of providing a structured and modular way to discover and share data across spatial data across the web. And what's interesting is that and there's a number of these that have been already developed to cater for, I guess, the conventional spatial data infrastructures, things like point and vector data sets through features, through raster data through coverages, tiles. We've got maps, and there's a whole and a growing list of different APIs to target different data applications. And DGGS infrastructures are no different. They can, and one of the interesting things about DGGS is that they are so flexible that they can already take advantage of these conventional existing APIs without any problem. So you can ingest data into a DGGS using these conventional APIs. You can export data to these and sort of send maps to an ArcGIS instance or a QGIS instance. You can and have it interpret that and display it quite fine, which is really neat. It lowers the barrier to access to DGGS infrastructures, and it means that in most cases people will be using DGGS without even knowing. However, we do lose the direct access to the DGGS topological and analytic functions, and these are functions that allow us to do more with the data than what we can do with the conventional APIs. And this is the primary justification and requirement for an OGC API for DGGS to be defined, one that is consistent with and marries nicely into the modular sort of API sort of landscape, but allows for those who want to take advantage of that, of the advanced DGGS capabilities, to be able to do that directly through an API without having to implement their own server infrastructure, which is a good thing. So where we are at the moment. So I'll just give a brief overview of what the DGGS API currently looks at. We're in sort of the draft stage of defining this specification document. Now we've got the referencing for that is stored in this GitHub repository here, and there is a Swagger Hub view of that here. For those who get access to the slide deck, this will be a link. It was just really long and ugly, so I just sort of masked it. But fundamentally, there's a bunch of different conformance classes that currently exist. First being, I guess, a core conformance class, or a common, which basically is just leveraging most of the common APIs that are out there: landing page, document definition, data collections that are available on that server instance. In this case, here a list of DGGS implementations that are available, but all of these are sort of following the OGC API common sort of pattern and framework. Then we have data collections, and again, we haven't done anything different here, and this is included more so for completeness than anything else. But yeah, this is no different to coverages or features, but it's a place to store your data, your collections. Then we get into the DGGS definition. So this, in many regards, is a representation or a direct reference and link back to the DGGS, the fundamental DGGS standards. How do we define the particular DGGS that we're dealing with? How do we traverse up and down that DGGS hierarchy? And the other interesting thing here, which is why I've got these in bold, is that the DGGS API is designed to be transportable. So if we're dealing with and wanting to interrogate a DGGS structure itself, just up and down, and look at it, see what it's all about, we can do that. If we move that and tack it onto the end of a collection, we're now dealing with the DGGS and view or enablement of that collection. And so we start to look at things like the DGGS zones that data maps to, rather than just a generic, give me all of the zones. and that's an important aspect and flexibility sort of thing. And there's one thing that we're actually currently validating and refining this approach. So this is quite a moving feast. But the last two bits here are probably the really critical things. We've got the data retrieval, which is asking the question of what is here. So we start with our DGGS sort of path. We tack on data. So we're now looking at, well, what's the data here? What's the data at the whole DGGS or the DGGS level? What's the data in a particular zone or tagged or mapped to a particular zone? Or if we're looking at it from the perspective of a collection, what is happening inside this collection in terms of the DGGS, but from the data perspective. The zone query is answering the fundamental spatial question of where is it? And so this, where we're able to search and apply these topological functions in a very simple and consistent way. Now, like I said before, the OGC API for DGGS is a moving feast. It's undergoing rapid development, and in fact, this week is the 16th OGC API code sprint, which is focusing on space partitioning code systems, including discrete global grid systems, but not limited to that. And so that's currently on at the moment, and we're actually building and testing this specification out with the primary goal of providing this consistent, easily and common window into any DGGS. It doesn't matter what DGGS we're dealing with. In the back end, the front end developers, they only have to work with the DGGS API in order to enable these advanced capabilities. And I guess something I didn't sort of mention earlier, the ability of DGGS to I guess aggregate or condense complex multidimensional problems into one-dimensional array set theory is one aspect of that is the ability to turn these complex operations into a simple database lookup without the need of any spatial data add-ons or any data resampling or reprojecting in order to compare apples and apples or rasterization, vectorization schemes. Through smart use of DGGS infrastructures, all of this can be achieved purely by a database index lookup. What are the zones I'm interested in? Give me all the data for those zones. And you can do that across multiple collections, across multiple server infrastructures, across multiple servers, any sort of around the world. And I guess the importance of having a consistent API that plugs nicely and consistently into the wider suite of spatial APIs is exactly to enable that machine-to-machine scalability of DGGS enablement. So I've probably gone a little bit over time, but thank you all. And if there's any questions, I'm happy to field them.
Thank you, Matthew. That was really interesting. And now all of a sudden I understand why Kathy was asking questions, and it also makes sense why she was asking this behind the schools regarding his previous presentation. Please, are there any questions from somebody in the room regarding this DGGS? Kathy?
I've talked it all through with Matt many times.
Yeah, no, I understand now. Okay, let's just see if there's any questions online. Are there any questions from any of the online participants to Matthew in this regard? No one. Matthew, thank you very much.
No worries. Thank you.
I'm sure your presentation will be available to everybody who is online today, as well as the people in Polaris group. Something that is really interesting. I do have actually a question. Maybe it's not really specific about your DGGS. I've heard about, I've read about it and I've seen it online. What 3 words? Is that something that you is that something that you work with? Is it also something related to what you do?
So what 3 words falls into, I guess, a category of DGGS-like infrastructures. And with the expansion of the DGGS suite of what is considered under the umbrella of DGGS, the one thing that limits what 3 words is that the current implementation of it is single resolution, and so there is no sort of spatial aggregation or disaggregation, zooming in and out of cells or zones, which means that what 3 words is a discrete global grid as opposed to a discrete global grid system, and it's primarily, I mean, the implementation of what 3 words and the typical use case application for that infrastructure is primarily around navigation and location. That's why earlier on I said, well, it's sort of these things can be used for that. They're not primarily used. Now, I mean, because if we look at what 3 words has, it's a tessellation of the entire globe, with the exception of they because of the way they've structured it, they have to do some funny stuff at the poles. But again, when you think about it, their business model is around addressing and postal addressing. Most people are not living in those areas where their grid system has some issues. Each cell has a unique identifier. Now it's not the same as most other DGGSs, but it still is a fixed a fixed sort of schema, and they actually have like a map and a schema of how each and every one of those cells is assigned a three value word, a three word sort of index. Now, I mean, part of their innovation is all about actually getting the phonics and the structure of those words so that their application and use through spoken communication is as clear as possible. So that's sort of the area they've gone down. But notionally, each cell is more or less the same size, is around 4 meters, and allows sort of for many of these. But one thing that limits them from being able to, I guess, wear the badge of a DGGS is that the what 3 words grid is single layer, single resolution, and so if you're wanting to use that for data and combining data at multiple resolutions, then that particular discrete global grid would not be a good choice. But for the use cases that what3words are targeting with their business model, that's perfectly fine.
Thank you very much for the very detailed explanation. Thanks. Good. We are now at the end of our discussions and for this day. I don't see that there are any more. Are there any more comments from the audience online or in Doris? Good. Then I say thank you very much. We do have some information that we would like to give to Doris Room before we leave today regarding tonight. But I would like to say thank you to all our participants online. Have a nice evening or morning. Thank you, Matthew. Bye-bye.
No problem. Thanks.